Welcome to The Explainer. Today, we're diving into a question that sounds like it's straight out of science fiction, but what if it's our reality? We're going to play cosmic detectives, following a trail of some really powerful formulas to see if our entire universe might actually exist inside a black hole.
So let's just jump right in. It's a wild idea, right? But a really fascinating theory suggests that our universe might be exactly that. It proposes that the Big Bang wasn't the absolute beginning, but more of a transformation, the result of a colossal star collapsing in some kind of parent universe, which in turn created our own. All right, so how do we even begin to investigate something like this? Well, our first clue doesn't come from peering out into the cosmos. Nope, it comes from looking at the very fabric of time itself.
And that leads to this first startling idea. What if time for us, right here inside our little bubble of space-time, is running differently than it would for someone, hypothetically on the outside? There's a calculation that suggests our cosmic clock is ticking at a completely different pace. According to the math, our reality is kind of in slow motion. Time inside our universe runs about 27% slower than it would in an exterior space. So think about that. While we've experienced 13.8 billion years since the Big Bang, an outside observer would have only counted about 10 billion. And look, this isn't just some random number pulled out of a hat. It comes directly from this time dilation formula. It tells us that the slowing of time, that's the delta T over T, is directly connected to two huge things: the density of exotic energy, like dark energy, which is that rho symbol, and the sheer size of our universe, the R squared. This is our first big clue. The very stuff and scale of our universe are actually warping time, making it a unique place with its own set of rules. Okay, so to understand how a universe could be born from a black hole, we need to decipher two key pieces of a kind of cosmic code. You can think of these equations as our Rosetta Stone, letting us translate the universe we see into the physics of what might have created it. So our first piece of the code is something called vacuum impedance. Now, the easiest way to think about it is like the electrical resistance of empty space. Here in a lab on Earth, empty space actually resists the flow of energy. It has a value of about 377 ohms. But when you calculate this for our entire cosmos, the number is, well, it's practically zero. This is huge. It suggests our universe isn't a resistor at all, it's a cosmic superconductor, letting energy flow almost perfectly. And check this out. Here's how we get that number. This formula, V equals C squared over P, is just beautiful. It's so simple. It says the vacuum impedance, V, is just a constant, the speed of light squared, divided by P, which is the total power flowing through the entire universe. And since the total power of our cosmos is absolutely enormous, when you divide by that huge number, you get a result that's basically zero. This is a critical clue. Our universe is fundamentally built to be incredibly efficient at moving energy. Now, for the second piece of the code, this idea of an energy cascade. The best way to picture it is like a cosmic snowball effect. You start with one tiny little seed of energy, the E input. Then, the basic properties of our universe act like these massive amplifiers. First, cosmic resonance makes it vibrate and grow. Then quantum fluctuations at the tiniest scales add even more energy. Then the cosmic expansion itself stretches and boosts it. And finally, the very geometry of space-time magnifies it again. Each step just multiplies that initial energy into something absolutely colossal. So let's just quickly recap our clues. Time in our universe runs slow, the vacuum of space is like a superconductor, and a tiny bit of energy can be amplified into something massive. So now, for section 3, let's see what kind of picture these clues paint when we put them all together. Here is the key insight, the big aha moment. What if that mysterious dark energy that's pushing our whole universe apart isn't really that mysterious? What if it's just the final amplified output from that cosmic energy cascade we were just talking about?
And this is so cool because it gives us an amazing tool. We can actually measure the total amount of dark energy in the universe today. And since we think we know the amplification process, we can run the whole calculation in reverse to figure out just how big that initial seed of energy must have been.
And when you run the numbers, the result is just staggering. The calculation points to an initial energy seed that's equivalent to the mass of 29 million of our suns. And this question leads us right to our prime suspect. What kind of object fits that description? A primordial, supermassive black hole. The theory suggests that the collapse of an object this size,
in a parent universe, could have provided the seed energy for literally everything we see around us.
What's just remarkable here is how neatly all the numbers fit together. This table shows the specific values for the universe's base resonance, its quality factor, the input power, and the total amplification. Now get this, when you multiply all these different cosmic parameters from the model together, they perfectly equal a fundamental constant of nature, the speed of light squared. It's like finding a hidden mathematical symmetry in the universe, which really suggests the model is on the right track. Okay, this is an absolutely fascinating story, but is it just a story? Is it all just math on a whiteboard? Well, for our fourth section, we have to ask, could we find actual evidence for this out there in the cosmos? Because a good scientific theory has to make predictions you can test, and this one is no different.
So this theory makes some really specific predictions that an observatory like the James Webb Space Telescope could actually look for. First, an extra redshift in the light coming from the very edge of the universe, caused by that 27% time dilation. Second, you'd look for strange patterns in the cosmic microwave background, the universe's baby picture, that could be echoes of the parent black hole's collapse. And finally, it makes a really precise prediction about the nature of dark energy itself.
But maybe its most powerful success is this. The theory predicts how dark energy should behave, a value cosmologists call W. The theory calculates W to be about -1.03. And unbelievably, that is an exact match for what our most recent astronomical observations are actually measuring right now. That's not just close, that's a direct hit. It's a stunning piece of evidence.
For our final section, let's just zoom all the way out and look at the grandest implication of this whole idea, the ultimate timescale, and maybe the fate of our entire universe. If our universe was created this way, the model basically treats it like a giant resonant cavity. You can almost think of it like a musical instrument. And just like a guitar string has a fundamental note it likes to vibrate at, the universe should have a fundamental frequency of its own. And you can do that calculation. The time it would take for our universe to complete one full cosmic vibration is a mind-boggling 290 billion years. Now, to put that into perspective, our universe is currently only 13.8 billion years old. What this implies is that everything we know, the entire history of the cosmos, is just the first phase of this grand cycle. We are living in the universe's first great expansion. You could call it the cosmic inhale. We are not even halfway through the very first breath. And that leaves us with one final, truly provocative question. This model suggests the current acceleration isn't going to last forever. If this expansion, this cosmic inhale, is eventually followed by a contraction, a great exhale, what does that mean for the ultimate fate of everything? And could that collapse, in turn, become the seed for the next universe in an eternal cycle?